Tonight, as you settle into the quiet comfort of wherever you find yourself, I want you to imagine something impossible. Picture yourself shrinking down, smaller and smaller, until you're no more than a speck of dust floating in your room. From this tiny perspective, your house would seem like an entire world. The distance from your bedroom to the kitchen might as well be a journey across continents. Your neighborhood would stretch beyond the horizon like an endless landscape of towering structures and vast spaces. Now imagine shrinking even further. Your entire city becomes a sprawling metropolis that you could never hope to explore in a lifetime. Your country transforms into something so vast that even traveling at the speed of light, it would take precious moments to cross, and your planet, Earth itself, becomes this magnificent sphere, hanging in darkness, so large that you couldn't comprehend its true size. But here's where things get truly mind-bending. Even at this impossible scale, we haven't even begun to grasp the size of our cosmic neighborhood, because Earth, for all its majesty, is nothing more than a grain of sand on an infinite beach when compared to the galaxy we call home, the Milky Way. If you find comfort in these gentle explorations of cosmic scale, I'd be grateful if you'd consider subscribing and liking this video. The visuals are here for you, but feel free to close your eyes, breathe deep, and let your imagination drift through the vast expanses we're about to explore together. Also, I'd love to know where you're contemplating the cosmos from tonight. Comment your time and location below. The question of how big the Milky Way actually is isn't just an exercise in numbers. It's a journey into the very nature of space, time, and our place within something so incomprehensibly vast that our minds struggle to contain it. We're about to embark on a voyage of scale that will stretch your imagination to its absolute limits, because understanding the true size of our galaxy requires us to think in dimensions that dwarf everything we know about distance and space. Let's begin this cosmic journey by establishing our starting point. Right now, as you listen to these words, you're sitting on a planet that measures roughly 12,800 kilometers across. That's already a distance so large that it would take you several months to walk from one side to the other, assuming you could somehow walk on water and through solid rock. The circumference of our Earth stretches for over 40,000 kilometers. If you could drive a car around the equator at highway speeds without ever stopping, it would take you more than 2 weeks of continuous driving. But Earth, vast as it seems to us ground-dwelling creatures, occupies just a tiny fraction of our solar system. The distance from our planet to the Sun spans approximately 150 million kilometers. Astronomers call this distance an astronomical unit, or AU, and it serves as our first stepping stone into cosmic measurements. Light itself, traveling at nearly 300,000 kilometers ahead, takes over 8 minutes to make this journey from the Sun to Earth. If we were to scale our solar system down so that Earth was the size of a marble, the Sun would be a ball about the size of a large beach ball, positioned roughly 26 minutes away, and Pluto, that distant dwarf planet at the edge of our solar system, would be another small marble located nearly a full kilometer from our beach ball Sun. Our entire solar system, from the Sun to the outermost reaches of the Oort cloud, where comets originate, spans roughly 100,000 AU, or about 15 trillion kilometers. These numbers are already challenging our ability to visualize them meaningfully. But here's where our journey into cosmic scale truly begins to boggle the mind. Because our entire solar system, vast beyond our everyday comprehension, represents nothing more than a microscopic speck when placed within the context of the Milky Way galaxy. To help us grasp these scales, astronomers had to develop new units of measurement. The distances between stars are so enormous that even our astronomical units become unwieldy. Instead, we measure interstellar distances in light years. A single light year represents the distance that light travels in 1 year, roughly 9.5 trillion kilometers, or about 63,000 AU. The nearest star to our Sun, Proxima Centauri, lies approximately 4.2 light-years away. This means that the light you see from this star tonight actually left its surface over 4 years ago, when you were younger, when the world was different. If our Sun were the size of a grain of sand, Proxima Centauri would be another grain of sand located roughly 4 kilometers away. The The space between these grains would be almost perfectly empty, a void so complete that it challenges our understanding of nothingness. But even this nearest stellar neighbor represents just the beginning of our galactic journey. The Milky Way contains not just a few hundred stars, not just a few thousand, but somewhere between 200 billion and 400 billion individual stars, each one potentially hosting its own family of planets, each one a sun that could warm worlds we'll never see. The structure of our galaxy resembles a vast spiral, like a cosmic hurricane of stars slowly rotating through space. If we could somehow position ourselves far above the Milky Way and look down upon it, we would see elegant spiral arms sweeping outward from a bright central bulge. These arms contain most of the galaxy's star-forming regions, where new suns are born from collapsing clouds of gas and dust. Our solar system resides in what astronomers call the Orion Arm, sometimes known as the local spur. This is a minor spiral arm, a kind of cosmic side street compared to the galaxy's major thoroughfares. We're positioned roughly 26,000 light-years from the galactic center, about halfway between the center and the edge. In the grand scheme of the Milky Way, we occupy what might be considered the galactic suburbs. To put this distance in perspective, if you could somehow travel at the speed of light, it would take you 26,000 years to reach the center of our galaxy. The light we observe from the galactic core today actually began its journey toward Earth during the height of the last ice age, when our ancestors were still discovering fire and developing the first primitive tools. But the distance to the galactic center represents only part of the Milky Way's true dimensions. The galaxy stretches approximately 100,000 light-years from edge to edge. Imagine trying to cross this distance, even traveling at light speed, the fastest possible velocity in the universe. This journey would consume 100,000 years. 100,000 years ago, modern humans were just beginning to migrate out of Africa and spread across the globe. The disk of our galaxy, where most of the stars reside, measures roughly 1,000 light-years thick. While this might seem thin compared to the galaxy's overall diameter, it still represents a volume of space so vast that it contains hundreds of billions of stars. If we could somehow compress all of human history into a single second, it would still take nearly 3 hours to cross the thickness of the galactic disk at light speed. Surrounding this stellar disk lies the galactic halo, a roughly spherical region that extends perhaps 200,000 light-years from the galactic center. This halo contains globular clusters, ancient collections of stars that formed when the galaxy was young, as well as vast amounts of dark matter, whose presence we can detect, but whose nature remains mysterious. The total mass of the Milky Way defies easy comprehension. Astronomers estimate that our galaxy contains somewhere between 800 billion and 1.5 trillion times the mass of our Sun. To put this in perspective, our Sun alone weighs about 2 Kai's 10 Kukulgane, a 2 followed by 30 zeros, a number so large that even writing it out fully would consume several lines of text. But mass and size tell only part of the story of our galaxy's true scale. The Milky Way is also ancient beyond our ability to fully grasp. Current estimates suggest that our galaxy began forming roughly 13.6 billion years ago, less than 200 million years after the Big Bang itself. This means that the Milky Way has existed for over 95% of the universe's entire history. During this vast span of time, our galaxy has been in constant motion. The entire Milky Way rotates, but not like a solid wheel. Different parts of the galaxy complete their orbits at different speeds, creating the spiral structure we observe. Our solar system, located in the galactic suburbs, takes approximately 225 million years to complete one orbit around the galactic center. This orbital period is sometimes called a galactic year, and it provides another way to appreciate cosmic timescales. Since Earth formed about 4.6 billion years ago, our planet has completed roughly 20 trips around the galaxy. When dinosaurs ruled the Earth, we were on the opposite side of the galaxy from where we are today. The last time our solar system was in its current galactic position, mammals were tiny creatures scurrying between the feet of reptilian giants. As our galaxy rotates, It's also moving through space at tremendous speed. The Milky Way is falling toward the Andromeda Galaxy, our nearest large galactic neighbor, at roughly 11. This cosmic collision, scheduled to occur in approximately 4.5 billion years, will reshape both galaxies into something entirely new. But even as we contemplate these mind-bending scales of space and time, we must remember that the Milky Way itself represents just one galaxy among hundreds of billions throughout the observable universe. Our cosmic home, vast beyond imagination, is itself merely a single note in a symphony of galaxies that stretches to the very limits of what we can observe. The numbers we use to describe the Milky Way's size push the boundaries of human comprehension. When we say that our galaxy spans 100,000 light-years, we're describing a distance so vast that light itself, the fastest thing in the universe, requires 100,000 years to cross it. When we speak of billions of stars, we're talking about numbers larger than the total count of every grain of sand on every beach on Earth. Yet, perhaps the most remarkable aspect of the Milky Way's scale isn't just its enormous size, but the fact that we, as temporary arrangements of atoms on a small rocky planet, have somehow managed to measure it. We've mapped the spiral arms, counted the stars, calculated the mass, and determined our position within this vast cosmic structure. We are the galaxy becoming aware of itself, matter organized in such a way that it can contemplate its own cosmic home. As we continue our exploration of the Milky Way's true dimensions, we'll discover that size is only the beginning of this galaxy's mysteries. We'll explore the violent processes occurring at its center, the stellar nurseries where new stars are born, and the dark matter that provides the invisible scaffolding holding everything together. Tonight, we venture deeper into the architecture of our cosmic home, where the very concept of distance becomes almost meaningless in any human sense. Because when we truly begin to explore the Milky Way's structure, we discover that our galaxy isn't just large, it's organized in ways that reveal the elegant complexity of cosmic evolution itself. Picture, if you will, the galactic center, that brilliant heart of our cosmic spiral, located 26,000 light-years away. At this distance, even our most powerful telescopes struggle to peer through the veils of dust and gas that obscure our view. But what lies hidden there represents one of the most extreme environments in the known universe. At the very core of the Milky Way lurks a supermassive black hole called Sagittarius A, a gravitational monster containing the mass of over 4 million suns, compressed into a region smaller than our solar system. This central black hole doesn't exist in isolation. It's surrounded by a dense cluster of ancient stars, some of which orbit so close to the black hole that they complete their circuits in just 16 years, racing through space at speeds that approach a significant fraction of light speed itself. These stars experience gravitational effects so extreme that Einstein's theories of relativity become essential for understanding their motion. Surrounding this central bulge, the galaxy extends outward in 4 major spiral arms, each one a river of stars, gas, and dust flowing through space in elegant curves that span tens of thousands of light-years. The Perseus arm, the Sagittarius arm, the outer arm, and the Scutum Centaurus arm each contain billions of stars in various stages of their cosmic life cycles. Our own Orion arm, where Earth makes its home, connects these major spiral structures like a bridge spanning cosmic rivers. Even this minor arm contains enough stars to boggle comprehension. Within just a few thousand light-years of our solar system, astronomers have catalogued hundreds of thousands of individual stars, each one a potential source of worlds, of chemistry, of possibilities we can barely imagine. But the spiral arms themselves are not permanent structures frozen in space. They're more like waves moving through the galactic disk, regions of higher density that trigger star formation as they sweep through the galaxy's rotation. Stars are born within these arms, live out their lives, and often drift away from their birthplaces as the galaxy continues its ancient rotation. Our own sun likely formed within a spiral arm billions of years ago, and has since migrated to our current position between major arms. The process of star formation within these spiral arms creates some of the most spectacular structures in our galaxy. Giant molecular clouds, each one containing enough material to create thousands of stars like our Sun, collapse under their own gravity to birth entire stellar neighborhoods. These star-forming regions, with names like the Eagle Nebula, the Orion Nebula, and the Carina Nebula, represent cosmic nurseries where the raw materials of the universe transform into the nuclear furnaces that light up the galaxy. The scale of these stellar nurseries challenges our ability to visualize them meaningfully. The Eagle Nebula, famous for its pillars of creation, spans roughly 70 by 55 light-years. Within this single star-forming region, astronomers estimate that hundreds of new stars are currently being born. Each pillar of gas and dust towers several light-years high, containing material that will eventually collapse to form multiple star systems. As we map these structures throughout the galaxy, we begin to appreciate that the Milky Way isn't just a collection of individual stars, but a vast ecosystem of cosmic processes. Massive stars live fast and die young, exploding as supernovae that scatter heavy elements throughout the galaxy and trigger new waves of star formation in nearby molecular clouds. Smaller stars, like our Sun, burn steadily for billions of years, providing stable energy sources that might nurture the development of complex chemistry and potentially life itself. The chemistry of our galaxy tells a story of cosmic evolution that spans billions of years. When the Milky Way first formed, it contained primarily hydrogen and helium, the simplest elements created in the Big Bang. But as generations of stars lived and died, they forged heavier elements in their nuclear cores and scattered these materials throughout the galaxy when they expired. Today, our solar system contains elements like carbon, oxygen, silicon, and iron that were created in the hearts of stars that lived and died billions of years ago. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were forged in stellar furnaces and scattered across the galaxy by ancient supernovae. In a very literal sense, you are made of star stuff, your atoms having journeyed across vast reaches of space and time before finding their temporary arrangement in your body. This process of chemical enrichment hasn't occurred uniformly throughout the galaxy. The central regions, where star formation has been more active over cosmic time, contain higher concentrations of heavy elements than the outer reaches. Astronomers can actually map the chemical evolution of the Milky Way by studying the composition of stars at different distances from the galactic center. The outer regions of our galaxy present their own mysteries and marvels. Beyond the visible disk of stars lies the galactic halo, a roughly spherical region populated by some of the oldest objects in the galaxy, globular clusters, each containing hundreds of thousands of ancient stars, orbit through this halo like cosmic cities, following elliptical paths that take them far above and below the galactic plane. These globular clusters represent time capsules from the early universe. The stars within them formed when the galaxy was young, and their compositions reflect the chemical conditions that existed over 10 billion years ago. By studying these ancient stellar populations, astronomers can peer back through time to understand how the Milky Way evolved from a chaotic cloud of primordial gas into the structured spiral galaxy we observe today. The halo also contains vast amounts of dark matter, that mysterious substance that makes up roughly 85% of all matter in the universe, but interacts with ordinary matter only through gravity. The dark matter halo of the Milky Way extends far beyond the visible stars, creating a gravitational framework that holds the galaxy together and influences the motion of everything within it. Current models suggest that our galaxy's dark matter halo might extend 300,000 light-years or more from the galactic center, making the true size of the Milky Way much larger than the visible spiral of stars would suggest. Within this vast halo, the luminous matter we can observe, all the stars, gas, and dust that create the galaxy's spectacular spiral structure, represents less than 20% of the total mass. As we orbit through this cosmic structure at 2020 km/s, our solar system experiences the galaxy not as a static backdrop, but as a dynamic environment that has shaped the history of our planet. In ways we're only beginning to understand, our motion carries us through different regions of the galactic disk over millions of years, exposing Earth to varying levels of cosmic radiation and potentially influencing climate and evolutionary patterns. Some scientists have proposed that our solar system's passage through the galaxy's spiral arms might correlate with mass extinction events in Earth's history, though this remains a topic of active research and debate. What's certain is that our planet's 4.6 billion year journey through the Milky Way has carried us through a constantly changing cosmic environment. The galaxy we inhabit today is also quite different from the Milky Way of the past. Billions of years ago, when the galaxy was younger, star formation rates were much higher, creating a more chaotic and energetic environment. The supermassive black hole at the galactic center was likely much more remote, consuming material and launching powerful jets of energy that would have made the galaxy's core region inhospitable to life as we know it over cosmic time. The Milky Way has also grown through mergers with smaller galaxies. Astronomers can identify the remnants of these ancient collisions in the form of stellar streams, long trails of stars that were torn from smaller galaxies as they were consumed by our larger galaxy's gravitational field. Currently, the Milky Way is in the process of consuming several smaller satellite galaxies, including the Large and Small Magellanic Clouds, which are visible from Earth's southern hemisphere. These cosmic meals add mass to our galaxy and trigger new episodes of star formation. As the disrupted gas and dust from the smaller galaxies compress and collapse, the three-dimensional structure of the Milky Way continues to reveal new complexities as our observational capabilities improve. Recent surveys have discovered that the galactic disk isn't perfectly flat, but shows subtle warping, particularly in its outer regions. This warping might result from gravitational interactions with satellite galaxies or the influence of the galaxy's dark matter halo. We've also discovered that the Milky Way possesses a central bar structure, an elongated concentration of stars that extends roughly 27,000 light-years from the galactic center. This bar rotates more slowly than the outer spiral arms and may play a crucial role in channeling gas toward the galaxy's center, feeding the central black hole and influencing the overall dynamics of stellar formation. As we contemplate these vast scales and complex structures, we begin to appreciate that our question of how big the Milky Way really is doesn't have a simple answer. The galaxy's size depends on what we're measuring and how we define its boundaries. The visible spiral of stars extends roughly 100,000 light-years across, but the total gravitational influence of the galaxy reaches much farther into space. The boundaries of our cosmic home blur into something even more mysterious when we consider the Milky Way's invisible architecture. Beyond the furthest visible stars, beyond even the ancient globular clusters that mark the outer reaches of the stellar halo, lies a vast sphere of influence that extends perhaps 1,000,000 light-years from the galactic center. This is the domain of dark matter, that enigmatic substance that shapes the galaxy's structure while remaining completely invisible to our eyes. Within this dark matter halo, smaller galaxies orbit our own like cosmic moths, drawn to a gravitational flame. The Magellanic Clouds, visible as fuzzy patches in the southern sky, are perhaps the most famous of these satellite galaxies, but they represent just two members of a much larger family. Astronomers have discovered dozens of smaller dwarf galaxies bound to the Milky Way, each one containing millions to billions of stars, each one following its own orbital dance around our galactic center. These satellite galaxies help us understand the true scale of the Milky Way's gravitational reach. The most distant confirmed satellite galaxy lies over 400,000 light-years away, yet it remains gravitationally bound to our galaxy, slowly orbiting through space over periods of billions of years. At this distance, the gravitational influence of the Milky Way is so weak that these satellites barely feel our galaxy's pull, yet it's still strong enough to keep them from escaping into the void between galaxies. But even as we map these distant satellites, we must grapple with the reality that our understanding of the galaxy's true size continues to evolve. New telescopes reveal fainter and more distant structures. Advanced computer simulations suggest that the Milky Way's dark matter halo might extend even further than we previously imagined, perhaps reaching halfway to the Andromeda Galaxy itself. The space between galaxies, once thought to be empty, turns out to contain its own mysteries. Streams of gas and dark matter stretch between galactic neighbors, creating a cosmic web of connections that link our galaxy to the larger universe. These intergalactic bridges carry matter and energy across millions of light-years, suggesting that the Milky Way isn't an isolated island of stars, but part of a much larger cosmic ecosystem. As our galaxy rotates through this larger structure, It experiences tidal forces from neighboring galaxies that slowly distort its shape over cosmic time. The Andromeda Galaxy, our nearest large neighbor at 2.5 million light-years away, already exerts a measurable gravitational influence on the Milky Way's outer regions. Over the next 4.5 billion years, this influence will grow stronger as the two galaxies spiral toward their inevitable collision. This future merger will fundamentally transform both galaxies, creating a new elliptical galaxy that astronomers have already nicknamed Milky Way. The combined system will be larger than either galaxy alone, spanning perhaps 200,000 light-years across, and containing over 1 trillion stars. Yet, even this cosmic catastrophe will occur so gradually that any hypothetical observers on Earth would barely notice the change over the course of a human lifetime. The concept of galactic evolution reveals another dimension to our question about the Milky Way's size. The galaxy we inhabit today is quite different from the Milky Way of the past, and it will be different again in the future. 10 billion years ago, when the galaxy was young and actively forming stars at a much higher rate, it would have appeared brighter and more chaotic. The spiral structure we see today has developed over billions of years as the galaxy settled into its current configuration. Star formation within the galaxy follows patterns that span millions of years, creating waves of stellar birth that sweep around the galactic disk. These waves compress gas clouds and trigger the formation of new stars, which then live out their lives over millions to billions of years before dying and enriching the surrounding space with heavy elements. This cosmic recycling process has been ongoing for the entire history of the galaxy, gradually transforming the simple hydrogen and helium of the early universe into the complex chemistry we observe today. The Milky Way spiral arms themselves represent temporary structures that form and dissolve over periods of hundreds of millions of years. What we see as permanent features of our galaxy are actually density waves moving through the stellar disk, creating the appearance of spiral structure while individual stars drift in and out of the arms over time. Our solar system has likely passed through several different spiral arms during its 4.6 billion year journey around the galaxy. Within these spiral arms, the process of stellar evolution creates structures of breathtaking beauty and scale. Stellar associations, loose groups of young stars that form together from the same molecular cloud, can span hundreds of light years and contain thousands of individual stars. As these associations age, their member stars gradually drift apart, dispersing throughout the galaxy and carrying with them the heavy elements forged in their cores. The most massive stars in these associations live fast and spectacular lives, burning through their nuclear fuel in just a few million years before exploding as supernovae. These stellar explosions release more energy in seconds than our Sun will produce in its entire 10 billion year lifetime. The shock waves from supernovae carve out cavities in the surrounding gas that can extend for hundreds of light years, creating cosmic bubbles filled with hot ionized gas. Multiple supernovae occurring within the same region can create even larger structures called superbubbles, cavities in the galactic disk that can extend for thousands of light years. These superb bubbles allow hot gas to escape from the galactic disk into the halo above, creating a complex three-dimensional structure that connects the thin disk of stars to the vast spherical halo that surrounds it. The interstellar medium, the gas and dust that fills the space between stars, plays a crucial role in the galaxy's ongoing evolution. This material, enriched by countless generations of stellar deaths, provides the raw material for future star formation. The density and temperature of the interstellar medium vary dramatically throughout the galaxy, from the cold, dense molecular clouds where stars are born, to the hot, tenuous gas that fills the spaces carved out by stellar explosions. Mapping the distribution of this interstellar material reveals another layer of the galaxy's complex structure. Radio telescopes can detect the emission from hydrogen gas throughout the galactic disk, revealing spiral patterns that complement and sometimes differ from the spiral structure traced by visible stars. This gas disk extends beyond the stellar disk, suggesting that the Milky Way continues to accrete material from the surrounding intergalactic medium. The magnetic field of the galaxy adds yet another dimension to its structure. Charged particles flowing through space follow the galaxy's magnetic field lines, creating cosmic ray particles that travel throughout the galactic disk and beyond. This magnetic field helps confine some of the galaxy's hot gas, while allowing other material to escape into intergalactic space, influencing the galaxy's evolution over cosmic time. As we trace the Milky Way's influence further and further from its visible boundaries, we begin to appreciate that asking, "How big is the Milky Way?" is like asking, "How big is a forest?" The answer depends entirely on what we're measuring. Are we counting only the trees? Or do we include the soil that nourishes them, the animals that live among them, and the watershed that sustains the entire ecosystem? Similarly, the Milky Way encompasses not just its visible stars, but the entire gravitational, magnetic, and chemical environment that those stars have created over billions of years of evolution. The galaxy's influence extends through dark matter, halos, tidal streams, satellite galaxies, and the complex web of gas and energy that connects it to the larger cosmic structure. Recent discoveries have revealed that our galaxy exists within an even larger structure called the Local Group, a gravitationally bound collection of over 80 galaxies dominated by the Milky Way and Andromeda. This local group spans roughly 10 million light-years across and contains a total mass of perhaps 5 trillion solar masses. Within this group, the Milky Way and Andromeda are the two largest members, with dozens of smaller galaxies orbiting around them like planets around binary stars. But even the local group represents just a small part of an even larger structure called the Virgo supercluster, which contains thousands of galaxies spread across 1110 million light-years of space. Our local group sits near the edge of the supercluster, slowly falling toward its center under the influence of gravity. At this scale, the Milky Way becomes just one galaxy among hundreds of thousands, a single note in a cosmic symphony of unimaginable scope and complexity. The realization that our galaxy participates in these larger structures fundamentally changes how we think about its size and significance. The Milky Way isn't just a collection of stars floating in empty space, but a dynamic component of the universe's larger structures, connected to neighboring galaxies by streams of dark matter and influenced by gravitational forces that operate across tens of millions of light-years. As our understanding of these cosmic scales deepens, we discover that the question of the Milky Way's size touches on some of the most fundamental mysteries in astronomy. How do galaxies form and evolve? What role does dark matter play in shaping cosmic structure? How do the processes occurring within individual stars influence the evolution of entire galaxies over billions of years? These questions remind us that size in the cosmic sense isn't just about distance or volume. It's about understanding the intricate relationships that connect phenomena across vast ranges of scale, from the quantum processes occurring within stellar cores to the large-scale structure of the universe itself. The Milky Way represents a crucial link in this chain of cosmic understanding, large enough to contain billions of individual stellar stories, yet small enough that we can study its structure in detail. Tonight, as we drift deeper into contemplation of our galactic home, we find ourselves confronting not just the immensity of space, but the elegant complexity of cosmic evolution itself. The Milky Way's size becomes not just a number to memorize, but a gateway to understanding our place within the vast web of relationships that connects every atom in our bodies to the most distant structures in the observable universe. As we continue our journey through the vast architecture of our cosmic home, we encounter perhaps the most humbling realization of all. The Milky Way exists not as a static monument in space, but as a living, breathing entity that pulses with the rhythm of cosmic time. Every moment, as you rest in the quiet of your evening, our galaxy is transforming itself through processes so gradual that entire human civilizations rise and fall between the beats of its cosmic heart. Consider the stellar nurseries scattered throughout the spiral arms, where new stars are being born at this very moment. The Eagle Nebula, stretching across 70 light-years of space, contains enough raw material to create 10,000 stars like our Sun. Within its towering pillars of gas and dust, gravity is slowly compressing matter that will eventually ignite into nuclear fusion, adding new lights to our galactic neighborhood over the next few million years. But for every star being born, others are reaching the end of their cosmic journey. Red giant stars, swollen to enormous proportions as they exhaust their nuclear fuel, are gently puffing off their outer layers to create planetary nebulae those ethereal shells of glowing gas that stretch for light years around their dying stellar cores. These stellar deaths aren't endings, but transformations, returning processed materials to the galactic ecosystem, where they will eventually become part of new generations of stars and planets. The most massive stars meet more violent ends, exploding as supernovae with such tremendous force that they outshine entire galaxies for weeks or months. Each supernova explosion releases more energy than our sun will produce in 10 billion years, creating shock waves that race through the surrounding space at thousands of kilometers per second. These cosmic explosions carve out cavities in the interstellar medium that can span hundreds of light years, creating hot bubbles of ionized gas that gradually cool and mix with the surrounding material. Within the galactic center, even more extreme processes unfold around the supermassive black hole that anchors our cosmic spiral. Sagittarius A, containing the mass of over 4 million suns compressed into a region smaller than our solar system, occasionally flares with X-ray emission as it consumes nearby material. Stars that venture too close to this gravitational monster experience tidal forces so extreme that they can be torn apart, their matter streaming into the black hole's accretion disk in brilliant spirals of superheated plasma. The spiral arms themselves represent waves of star formation that sweep around the galaxy like cosmic hurricanes, compressing gas clouds and triggering new episodes of stellar birth. These density waves move at different speeds than the stars themselves, creating the illusion of permanent structure, while individual stars drift in and out of the arms over millions of years. Our own solar system likely formed within one of these spiral arms billions of years ago and has since migrated to its current position between major arms. But the Milky Way's activity extends far beyond the visible disk of stars. High above and below the galactic plane, fountains of hot gas rise from regions of intense star formation, carrying energy and material into the galactic halo. These galactic fountains can extend thousands of light years from the disk, creating a complex three-dimensional structure that connects the thin disk of stars to the vast spherical halo that surrounds it. The magnetic field threading through our galaxy guides the motion of charged particles, creating cosmic ray streams that flow throughout the galactic volume. These high-energy particles, accelerated by supernova shock waves and other violent processes, carry information about stellar explosions across vast distances, creating a kind of galactic nervous system that connects distant regions through invisible channels of energy and information. As our galaxy rotates, different regions move at different speeds, creating a complex pattern of motion that astronomers call differential rotation. The inner regions complete their orbits faster than the outer regions, gradually winding up the spiral arms and creating the beautiful patterns we observe today. This rotation also generates powerful magnetic dynamos that amplify and maintain the galaxy's large-scale magnetic field over billions of years. The chemical evolution of the Milky Way tells a story of gradual enrichment that spans cosmic time. When our galaxy first formed over 13 billion years ago, it contained primarily hydrogen and helium, the lightest elements created in the Big Bang. But as successive generations of stars lived and died, they forged heavier elements in their nuclear cores and scattered these materials throughout the galaxy when they expired. Today, the outer regions of the galaxy remain relatively poor in heavy elements, while the inner regions show the chemical signatures of billions of years of stellar processing. This metallicity gradient, as astronomers call it, provides a record of how star formation and stellar death have shaped the galaxy's composition over cosmic time. The elements in your body, forged in the hearts of ancient stars, carry within them the chemical history of our galaxy's evolution. The dark matter halo that surrounds and permeates our galaxy plays a crucial but invisible role in all these processes. This mysterious substance, which interacts with ordinary matter only through gravity, provides the gravitational scaffolding that holds the galaxy together and influences the motion of everything within it. Computer simulations suggest that without dark matter, the Milky Way would have dispersed into space long ago, unable to maintain its spiral structure against the disruptive forces of stellar motions and galactic rotation. Within this dark matter framework, smaller structures called subhalos orbit through the galactic volume like invisible satellites. Some of these subhalos may have captured ordinary matter during the galaxy's formation, becoming the dwarf galaxies we observe today. Others remain completely dark, detectable only through their gravitational influence on nearby stars and gas clouds. These tidal streams and gas flows suggest that the Milky Way exists in a state of constant exchange with its environment. Material flows inward from the intergalactic medium, feeding ongoing star formation in the galactic disk. Meanwhile, energetic processes within the galaxy drive material outward, enriching the surrounding space with heavy elements forged in stellar cores. The galaxy's rotation carries our solar system through this dynamic environment at 2020 km/h, completing one orbit around the galactic center every 20-25 million years. During Earth's 4.6 billion year history, our planet has completed roughly 20 of these galactic years, each one carrying us through different regions of the galaxy and exposing us to varying cosmic environments. Some scientists have proposed that our passage through different parts of the galaxy might influence Earth's climate and evolutionary history. As we move through spiral arms with their higher densities of massive stars and supernova explosions, our planet may experience increased cosmic ray bombardment that could affect atmospheric chemistry and cloud formation. While these effects remain speculative, they remind us that Earth's history is intimately connected to our galaxy's structure and evolution. The three-dimensional structure of the Milky Way continues to reveal new complexities as our observational capabilities improve. Recent surveys have discovered that the galactic disk shows significant warping in its outer regions, with some areas tilted by as much as 20 degrees from the main galactic plane. This warping might result from gravitational interactions with the large and small Magellanic Clouds, or from the complex dynamics of the galaxy's dark matter halo. We've also learned that the Milky Way possesses a boxy central bulge rather than the smooth elliptical structure once assumed. This bulge appears to be a bar-like structure viewed nearly end-on from our perspective, extending roughly 27,000 light-years from the galactic center and rotating as a rigid body. This central bar plays an important role in channeling gas toward the galaxy's center, potentially feeding the central black hole and influencing star formation in the inner regions. The stellar halo surrounding our galaxy contains some of the oldest objects in the universe. Globular clusters orbiting through this halo preserve samples of the primordial gas from which the first stars formed over 13 billion years ago. These ancient stellar cities, each containing hundreds of thousands of stars, follow highly elliptical orbits that carry them far above and below the galactic plane, providing unique perspectives on the galaxy's overall structure. Between the globular clusters, individual halo stars trace the gravitational potential of the galaxy's dark matter distribution. These stars often pour in heavy elements because they formed before significant stellar processing had occurred, provide clues about the conditions that existed when the Milky Way was young. Some halo stars may actually be refugees from smaller galaxies that were disrupted and consumed by the Milky Way during its growth. The outer reaches of the galactic halo blend gradually into the local group environment, making it difficult to define exactly where the Milky Way ends and intergalactic space begins. Tidal streams from disrupted satellite galaxies extend far beyond the main body of the galaxy, creating a complex web of stellar debris that traces the orbital histories of ancient galactic encounters. As we map these distant structures, we discover that the Milky Way's sphere of influence extends much farther than the visible stars would suggest. The galaxy's gravitational reach encompasses a volume of space over 1 million light-years across, within which smaller galaxies orbit like planets around a star. This vast region, dominated by invisible dark matter, represents the true extent of our galactic home. Within this enormous volume, the visible components of the Milky Way, all the stars and gas and dust that create the spectacular spiral structure we admire in astronomical images, occupy less than 10% of the total space. The rest is filled with dark matter, a substance so foreign to our everyday experience that we can describe it only by what it doesn't do. It doesn't emit light, it doesn't absorb light, and it doesn't interact with ordinary matter except through gravity. Yet, this invisible component shapes everything we see. The rotation curve of the galaxy, the way stars move in their orbits around the galactic center, can only be explained if most of the galaxy's mass exists in the form of dark matter. The beautiful spiral arms we observe owe their structure partly to density waves propagating through this dark matter distribution, Even the formation of our solar system may have been influenced by the local density of dark matter in our galactic neighborhood. The mystery of dark matter reminds us that our understanding of the Milky Way's size and structure remains incomplete. We can map the visible components with increasing precision, but the dominant component of our galaxy remains largely invisible to our instruments. Future generations of astronomers may discover that the Milky Way possesses structures and properties that we cannot currently detect or imagine. As we contemplate these vast scales and invisible architectures, we begin to appreciate that the Milky Way represents far more than a collection of stars. It's a complex ecosystem where matter and energy flow between components over timescales ranging from seconds to billions of years. Stellar winds carry processed material from dying stars into the interstellar medium. Shockwaves from supernovae compress gas clouds and trigger new episodes of star formation. Gravitational interactions between stars gradually heat the galactic disk and thicken it over time. The chemical elements that make up our bodies have participated in this galactic ecosystem for billions of years. The carbon atoms in your cells were forged in the cores of massive stars that lived and died before our solar system formed. These atoms were scattered into space by stellar winds and supernova explosions, mixed with other materials in the interstellar medium, and eventually incorporated into the molecular cloud that collapsed to form our sun and planets. In this sense, you are not separate from the Milky Way, but an integral part of its ongoing evolution. Your existence represents a temporary arrangement of galactic matter that has achieved the remarkable property of consciousness, allowing the galaxy to become aware of itself through your thoughts and perceptions. When you look up at the night sky and see the faint band of the Milky Way stretching across the darkness, you are seeing your cosmic home from the inside, recognizing the vast structure of which you are an inseparable part. The question of how big the Milky Way truly is thus becomes a meditation on the nature of cosmic connectivity. The galaxy's size cannot be measured simply in light years or solar masses, but must encompass the intricate web of relationships that connect every component to every other component across vast ranges of scale and time. From the quantum processes occurring within stellar cores to the large-scale motions of dark matter halos, the Milky Way represents a single integrated system whose properties emerge from the collective behavior of hundreds of billions of individual parts. As our journey through the galaxy's architecture continues, we discover that understanding its true size requires us to think not just in 3 dimensions of space, but in the 4th dimension of time as well. The Milky Way we observe today is the result of over 13 billion years of evolution, and it will continue changing for billions of years to come. The streams of time that flow through our galaxy carry stories written in starlight and shadow tales of cosmic transformation that unfold across scales so vast they make human history seem like a single heartbeat in an eternal symphony. As we drift deeper into the Milky Way's temporal architecture, we encounter a profound truth that reshapes our understanding of galactic size. Our galaxy exists not just in space, but across time, its dimensions stretching through billions of years of continuous evolution. Consider the ancient light that reaches us tonight from the galactic center. Those photons began their journey toward Earth 26,000 years ago, when our ancestors were painting cave walls and learning to navigate by the stars. The light carries within it a record of conditions that existed at the galaxy's heart during the height of the last ice age. In a very real sense, when we observe the galactic center, we're not seeing the Milky Way as it is, but as it was when mammoths roamed the Earth. This temporal dimension adds layers of complexity to our question about the galaxy's size. The Milky Way spans not only 100,000 light-years across space, but also reaches back through 13.6 billion years of cosmic history. Every photon of starlight that reaches our eyes carries information from a different moment in the galaxy's past, creating a view that combines multiple epochs into a single image. The stars we see in the night sky represent a kind of temporal fossil record, with each stellar population telling us about the conditions that existed when those stars formed. The oldest stars in the galactic halo pour in heavy elements and, following highly elliptical orbits, preserve information about the Milky Way's earliest epochs, when it was still assembling itself from smaller proto-galactic fragments. Meanwhile, the youngest stars, found primarily in the spiral arms, reveal the galaxy's current state of activity. These stellar nurseries, glowing with the light of newborn suns, show us that the Milky Way remains vibrant and dynamic, continuing to transform itself through ongoing star formation even after more than 13 billion years of evolution. The chemical gradients we observe throughout the galaxy tell a story of gradual enrichment that spans cosmic time. In the outer regions, where star formation has been less active, we find stars with compositions similar to the primordial gas from which the first stellar generations formed. Moving inward toward the galactic center, we encounter increasingly complex chemistry reflecting billions of years of stellar processing and element synthesis. This chemical evolution represents a kind of galactic memory, with each generation of stars building upon the legacy of those that came before. The iron in your blood connects you directly to supernovae that exploded billions of years ago when the galaxy was young and chaotic. The calcium in your bones was forged in stellar cores that no longer exist, their matter now distributed throughout the galactic ecosystem. But the Milky Way's temporal dimensions extend far beyond its past. The galaxy we inhabit today is destined for dramatic changes that will unfold over the next several billion years. The ongoing collision with the Andromeda Galaxy, already detectable through precise measurements of stellar motions, will fundamentally reshape both galaxies into something entirely new. Computer simulations of this future merger reveal a cosmic dance of unimaginable scope and beauty. Over the course of several billion years, the two galaxies will approach each other, their outer regions beginning to interact through gravitational tides. Stars will be flung into new orbits, some escaping into intergalactic space, while others fall toward the merged system's center. The supermassive black holes at the centers of both galaxies will eventually spiral toward each other, releasing gravitational waves that will ripple through space-time itself. When these cosmic monsters finally merge, they will create a single black hole containing the mass of over 100 million suns, surrounded by a brilliant accretion disk that will outshine the combined light of billions of stars. The resulting galaxy, which astronomers have nicknamed Milky, will be fundamentally different from either of its parent galaxies. Instead of the elegant spiral structure we see today, Milky will likely be an elliptical galaxy, its stars following chaotic orbits within a roughly spherical distribution. The organized star formation that currently occurs in spiral arms will cease, replaced by occasional bursts of stellar birth triggered by random encounters between gas clouds. Yet even this cosmic catastrophe represents just one chapter in the Milky Way's future evolution. After the merger with Andromeda, the resulting galaxy will continue to evolve, gradually consuming the remaining satellite galaxies in the local group and growing ever more massive. The star formation rate will slowly decline as the galaxy exhausts its supply of cold gas, eventually transforming Milky into a red and dead system populated primarily by long-lived, low-mass stars. On even longer timescales, the very stars that define our galaxy will begin to disappear. The most massive stars will exhaust their nuclear fuel within a few million years, exploding as supernovae or collapsing into black holes. Medium-mass stars like our Sun will expand into red giants before shedding their outer layers and fading to white dwarf remnants. Even the smallest red dwarf stars, which can burn for trillions of years, will eventually exhaust their hydrogen fuel and fade to darkness. These stellar life cycles operate on timescales that dwarf human comprehension. The longest-lived red dwarf stars will continue shining for 10 trillion years, a period 700 times longer than the current age of the universe. During this vast span of time, the galaxy will gradually darken as its stellar population ages and dies, eventually becoming a collection of stellar remnants orbiting through an increasingly empty void. But even as individual stars fade, the gravitational structure of the galaxy will persist for much longer. The orbits of stellar remnants, guided by the galaxy's dark matter halo, will continue for quadrillions of years, slowly decaying through gravitational wave radiation and occasional stellar encounters. The galaxy's shape will gradually evolve as these processes redistribute matter and energy throughout the system. On the longest timescales, even the protons that make up atomic nuclei may decay, causing the very matter of the galaxy to dissolve into elementary particles and radiation. But these processes operate on timescales so vast that they make the current age of the universe seem infinitesimally brief. Even if proton decay occurs, it will take 10 to 4 years or longer for the galaxy's matter to completely disappear. These future epochs reveal another dimension of the Milky Way's true size. The galaxy exists not just across the 100,000 light-years of space we can observe today, but across time scales that span from the earliest moments after the Big Bang to epochs so distant that they challenge our ability to comprehend them. In this temporal sense, the Milky Way is perhaps the largest single entity we can meaningfully discuss, its existence bridging nearly the entire history of the universe. The realization that we live within this vast temporal structure adds profound meaning to our cosmic perspective. The light from distant stars carries messages from the galaxy's past, while the processes we observe today will shape its far future. We exist at a special moment in galactic history, when the Milky Way has evolved complex chemistry and stable structures, but before it merges with Andromeda and begins its long decline towards stellar death. Our solar system's position within this temporal flow connects us intimately to the galaxy's evolution. The heavy elements that make Earth's complex chemistry possible were synthesized in stellar cores over billions of years before our solar system formed. The relatively stable galactic environment that has allowed life to evolve on Earth reflects the galaxy's current mature state, with well-developed spiral structure and regulated star formation. But our cosmic journey through the Milky Way continues, carrying us toward an uncertain future. As our solar system orbits the galactic center every 225 million years, we sample different regions of the galaxy, sometimes passing through spiral arms with their enhanced radiation environments, sometimes drifting through the quieter spaces between arms. The galaxy's rotation also carries us through different phases of its own evolution. When our solar system first formed 4.6 billion years ago, the Milky Way was more active, with higher rates of star formation and more frequent supernova explosions. The galactic environment that nurtured the development of life on Earth was different from the one we inhabit today, and it will be different again in the future. This cosmic context transforms our understanding of Earth's place in the universe. We are not passive observers of galactic evolution, but active participants in its ongoing story. The emergence of life on Earth represents a new chapter in the galaxy's development, the first time, as far as we know, that matter has organized itself in such a way that it can contemplate its own cosmic origins. The questions we ask about the Milky Way's size and structure are themselves part of the galaxy's evolution. Through our observations and theories, the galaxy becomes aware of itself, developing an understanding of its own properties and history. In a very real sense, human consciousness represents the galaxy's first attempt at self-reflection, matter organized in such a way that it can perceive and appreciate the cosmic structure from which it emerged. This perspective reveals that the Milky Way's size cannot be measured purely in physical terms. The galaxy encompasses not just stars, gas, and dark matter, but also the information and complexity that have emerged from its evolution. The genetic codes of Earth's organisms carry information about billions of years of evolution within the galactic environment. Human culture and science preserve knowledge about the galaxy's structure and history that exists nowhere else in the known universe. In this informational sense, the Milky Way has grown far beyond its original boundaries. Through space exploration and astronomical observation, human civilization has extended the galaxy's awareness beyond the solar system, creating a kind of galactic nervous system that connects Earth to the most distant observable structures. Our radio telescopes and space probes represent sensory organs that allow the galaxy to perceive itself with unprecedented clarity and precision. The digital storage systems that preserve our astronomical data contain detailed maps of the galaxy's structure, encompassing information gathered over centuries of observation. These databases represent a form of galactic memory, preserving knowledge about stellar motions, chemical compositions, and evolutionary processes that would otherwise be lost to time. As our understanding of the galaxy deepens, we begin to appreciate that its true size transcends any simple measurement of distance or mass. The Milky Way encompasses the entire web of relationships that connect its constituent parts across space and time. It includes the gravitational interactions that maintain its structure, the nuclear processes that power its stars, the chemical evolution that has created its complex composition, and the information processing that occurs within conscious minds like our own. This holistic view of galactic size suggests that we are not merely inhabitants of the Milky Way, but integral components of its ongoing evolution. Our thoughts and observations, our scientific theories and cultural expressions, our dreams and aspirations, all represent new forms of organization and complexity that have emerged from the galaxy's billion-year journey through cosmic time. The question of how big the Milky Way really is thus becomes a meditation on the nature of cosmic evolution itself. Size, in the deepest sense, is not just about spatial dimensions or temporal duration, but about the richness and complexity of the relationships that emerge from the interaction of countless individual components over vast scales of space and time. As we continue our exploration of these cosmic relationships, we discover that the Milky Way's influence extends far beyond its gravitational boundaries, reaching into the quantum foundations of reality itself. The elements forged in stellar cores obey the same physical laws that govern atoms throughout the universe. The gravitational waves produced by stellar collisions carry information about the galaxy's most violent events across cosmic distances. Even the vacuum of space within our galaxy is not truly empty, but filled with quantum fields that fluctuate according to principles established in the earliest moments after the Big Bang. These quantum processes connect the Milky Way to the fundamental structure of reality itself, making our galaxy part of a cosmic web of relationships that extends to the largest observable scales. The dark matter that dominates our galaxy's mass budget may consist of particles that interact through forces we have yet to discover. If so, the Milky Way serves as a laboratory for physics beyond our current understanding, its structure potentially revealing new principles that govern matter and energy on cosmic scales. The magnetic fields threading through our galaxy create channels for the flow of charged particles that connect stellar explosions to the interstellar medium and beyond. These invisible currents carry energy and information throughout the galactic volume, creating a form of electromagnetic that links distant regions through pathways of electric and magnetic force. As we map these various forms of cosmic connectivity, we begin to see the Milky Way not as a collection of separate objects, but as a single integrated system whose properties emerge from the collective behavior of its components. The galaxy's size, in this view, encompasses all the relationships and interactions that define its existence, from the quantum scale to the cosmic scale, from the briefest stellar flickers to the longest evolutionary timescales. This integrated perspective reveals that we are witnessing the Milky Way at a unique moment in its development, when it has achieved sufficient complexity to support the emergence of consciousness, but before the long decline that awaits all galaxies in the far future. We exist during a brief cosmic spring, when the galaxy blooms with stellar activity and harbors the conditions necessary for life and awareness to flourish. The privilege of this moment is not lost on those who pause to contemplate our cosmic circumstances. We live during the only epoch in galactic history when the universe is old enough to have developed complex chemistry, but young enough that stars still shine brightly and the cosmic web remains visible across vast distances. Future civilizations, if they exist, will inhabit a darker, colder universe, where the evidence for cosmic evolution has largely faded from view. Our observations of the Milky Way thus carry a special responsibility. We are documenting the galaxy during its prime, recording its structure and dynamics for potential future observers who may have access to far less cosmic information. The astronomical databases we create today may represent humanity's most lasting contribution to the galaxy's ongoing evolution, preserving knowledge that will remain valuable long after our civilization has passed into cosmic history. As we drift toward the conclusion of our journey through the Milky Way's vast architecture, we encounter a final humbling realization about the nature of cosmic scale. The galaxy we have explored together encompasses dimensions that stretch our minds to their limits. Yet it represents just one note in a cosmic symphony that includes hundreds of billions of other galaxies scattered throughout the observable universe. The local group, of which the Milky Way is a prominent member, contains over 80 galaxies bound together by gravity across a volume of space 10 million light-years in diameter. This entire group, vast beyond everyday comprehension, represents just a minor suburb in the Virgo supercluster, which spans 110 million light-years and contains thousands of galaxies. But even the Virgo supercluster, enormous as it is, forms just one component of even larger structures called galaxy filaments, cosmic rivers of matter that stretch across hundreds of millions of light-years, separated by vast voids that contain almost no matter at all. These filaments create a cosmic web that extends throughout the observable universe, connecting every galaxy to every other galaxy through an intricate network of gravitational relationships. Within this vast cosmic web, the Milky Way occupies a position of remarkable privilege. Located in a relatively quiet region between major galaxy clusters, our cosmic home has been able to evolve in relative peace, avoiding the violent interactions that can strip galaxies of their gas and halt star formation. This cosmic tranquility has allowed the complex chemistry necessary for life to develop and flourish within our galactic neighborhood. The question of the Milky Way's size thus opens onto questions about our place within the largest structures in the universe. We inhabit a galaxy that is simultaneously vast beyond human comprehension and insignificant within the cosmic web as a whole. This paradox of scale reveals something profound about the nature of cosmic existence. Significance does not depend on size, but on the complexity and beauty of the relationships that emerge from the interaction of countless individual components. In contemplating the true size of the Milky Way, we discover that we are part of something magnificent and mysterious that transcends our ability to fully comprehend it. Yet, in our very attempt to understand, in our persistent questioning and careful observation, we participate in the galaxy's ongoing evolution toward greater complexity and awareness. The Milky Way's size, measured in its fullest sense, encompasses not just the star's gas and dark matter that define its visible structure, but all the possibilities and potentials that emerge from its existence. It includes the countless worlds that orbit its hundreds of billions of stars, the complex chemistry that makes life possible, the information and consciousness that have emerged from its evolution, and the dreams and aspirations of any minds that might contemplate its beauty. Tonight, as you rest beneath the vast canopy of our galactic home, remember that you are not separate from the Milky Way, but an integral part of its ongoing story.